Thanks for joining us for another episode of Unposed Interviews with Physicists. Today, Jamie chats to a particularly charming physicist, and you'll see what we mean by that.
For British Science Week 2021, UMPO will be interviewing a number of academics and students amongst physics and mathematics. Today I'll be interviewing Dr. Marco Gersabeck, who's a particle physicist at the University of Manchester. So if you'd like to introduce yourself.
Yeah, thank you very much. My name's Dr. Marco Gersabeck. As you said already, I am working at the Large Hadron Collider at the LHCb experiment most of the time. And I lead the Manchester team working on that. We're almost 30 staff, scientists and PhD students working on that experiment. I'm also involved in a couple of other areas at the mu2e experiment at Fermilab. And I do some silicon R&D for possibly future upgrades, but also applications in areas outside particle physics.
So to start off, so what does your research focus on, and what are you currently working on? Obviously, you mentioned a few kind of collaborations and experiments there.
So in LHCb, obviously the whole team is very broad. We're one of the largest teams in the LHCb collaboration. And my personal research has been focused on charm physics for a long time now. So that's primarily looking, in my case, at charm mesons for the moment. So the D0 meson with a charm and anti-up quark. That's the main focus really. And what we're trying to do there is to understand the what we call the mixing behavior of these. That's when these mesons can turn into their anti-particle versions, and they then turn back. So this is a periodic process where they oscillate from their meson to their anti-meson and back, and that is a process that we know occurs in these mesons, but we haven't been able to measure it with great precision yet, and that is one of the main goals. And then building on top of that, we look for matter-antimatter differences. So as I mentioned already, mesons contain both matter and antimatter, so they're ideal laboratories for doing that. That is another key driver, and there we had a recent success in observing for the first time matter-antimatter differences in decays of these D0 mesons. And aside from that, one of the recent sort of, I don't want to call it highlights yet, but things that intrigue us very much are hints that in certain reactions, the leptons that are the electron with its heavier partners, the muon and the tau, don't behave in the same way. Within our current understanding, within what we call the standard model of particle physics, these should behave in the same way. However, we seem to get a number of hints that this is not the case, and that's a very exciting area. And there I'm involved also in a number of measurements that try to pin this down further and shed some light on what's going on there. And in parallel, I mentioned already detector R&D work. That is a very big thing in Manchester in general in our particle physics group. And our team is currently building the heart of the next LHCb experiment that is currently undergoing an upgrade, and we're building the detector modules that will sit right around the collision region of the LHCb experiment come next year. And so that's roughly what I do for LHCb. And then on mu2e, that is an experiment that looks for muon to electron conversions in nuclei. So you have muons that are being stopped in an atom. They basically replace an electron in the atomic shell, if you want. And then what we're looking for are these muons turning into electrons without the involvement of any neutrinos. Okay, so it's not a muon decay, which would emit a couple of neutrinos, but the neutrino-less version of this. And that's an extremely rare process. Within the standard model, you cannot observe that. So if we were to observe it, that would be a clear sign of physics beyond the standard model. And there are quite a few models that predict that. So it's a very high gain experiment, and there I'm involved in a small team where we're taking care of essentially the detector part that measures how many of these muon atoms we've formed. And thereby it sort of provides normalization for the measurement. Okay, so that's the other area, and then the R&D goes into future detectors where we may replace our vertex detector in sort of 10 years time. That's the plan, with a detector that can provide precise timing information as well. That's a huge challenge in the radiation environment that we have at the LHC, and that is something where we're with a few colleagues. I'm trying to provide a solution for that future detector.
So you've discussed what you do and kind of the research that you look into. I'm so curious as to what does the day or a day in the life of a particle physicist look like?
Right, there is no one typical day, because they're all extremely different. Right now, my days are very much filled with teaching activities, and I'm fortunate enough to teach actually a lot of particle physics as well. So today, I spent the whole morning remotely supervising a third-year laboratory experiment where our third-year students get to reanalyze LHCb data, and they get to reproduce a published LHCb analysis. They get to rediscover CP violations, so matter-antimatter asymmetries, in that case in B meson decay, so involving the bottom quark. And that's a very fantastic analysis, because it is on one hand fairly easy to reproduce, so the students do that over 8 lab days, but also they get fantastic signals out of that, huge matter-antimatter asymmetries that they can study, and they can appreciate the different steps that it takes to do such an analysis. And then for the rest, I obviously have a number of students and postdocs that I work with as well. And one of my students, she's now in her final year of her PhD, and she just gave a talk in a plenary session of the LHCb Collaboration Week that is ongoing this week. So that was a very proud moment to see her give that presentation there, which was extremely well received. And yeah, so with it is often working in small teams with students, with postdocs, but also likewise with engineers and technicians on the more hardware projects. And so I spend a lot of time in meetings with them. Obviously nowadays these are all virtual meetings, but nevertheless it's important to keep in touch and exchange ideas. And likewise, of course, also we have plenty of meetings with international collaboration to see where everyone is, exchange ideas, and of course eventually also discuss publications that are coming out and review each other's analyses before we submit them to journals and things like that.
So I'm also curious as to, obviously, people might have seen the Higgs boson, if sort of roughly about almost 10 years ago now, although it doesn't feel like that. May have heard of particle physics here and there. Obviously, they may know some electrons and things, but for a lot of people, they may not know very much about it. How would you kind of explain particle physics to the everyday person? How is it kind of relevant to them?
Right. Yeah. The Higgs boson is clearly very remote as a fundamental particle. But there are of course applications that grew out of particle physics, right? And a lot of particle physics is, for example, found in medical imaging techniques. That goes back to X-rays, if you want, but in modern techniques as well, like for instance the positron emission tomography. So what happens there? You use a radioactive nucleus that emits antimatter, anti-electrons, and what these do is they meet an electron of the material they are surrounded by, and then the positron and the electron annihilate and radiate off light. Okay, and what they radiate off are two photons, two light particles, whose energy is exactly the mass of the electron and the positron. They have the same mass. So we know exactly the energy of these photons that come out there, and they come out back to back. And then what happens is you have a detector surrounding a patient who you want to survey with that technique, and that detector detects these two photons on opposite sides arriving at the same time. And then if you do that multiple times, you record back-to-back photons multiple times. If you draw a line that's always connecting these, those lines that they will form a region of overlap, and that is where the where the origin of these photon lies, and that's how you can then identify. It's always often used to identify a cancer, because these radioactive particles tend to accumulate around cancerous regions. So you can map out a cancer with that. So that is a tool that has now been applied for some time. But where particle physics and even antimatter is very much at the heart of it. Something that is very much up and coming, that is also absolutely particle physics, is hadron therapy for as a cancer therapy. So that can be either with protons or also with heavier hadrons, like carbon nuclei, for example. And what you do there is you accelerate these through a particle accelerator, and then you shoot them onto the patient, and they have a very characteristic way of depositing their energy, and they do that predominantly in a well-defined spot that you can tune with simply the energy of the particle, and that allows you to attack a cancer in a well-defined region, leaving the healthy tissue before and after relatively unharmed, certainly compared to other techniques. And that is something where now there are a number of proton therapy centers up and coming. One in Manchester opened just about I think a year and a half ago or something like that, and where our accelerator colleagues were very much involved, but also colleagues from the particle physics group were involved in the diagnosis of the delivery of these protons, and also development of further techniques. So there we are in constant contact with our medical colleagues very often. There are other applications in security areas. Things like screening of lorries and so on is something that uses particle physics techniques. So there are a number of everyday applications that may not be completely obvious, but where particles are at play.
So obviously discussed your research and discussed particle physics. We've got quite a fun question next coming up, which is, what's your favourite particle and why? I suppose I should probably preface this with fundamental or otherwise.
Okay, fundamental, definitely the charm quark. So yeah, I mean, I've now been working on that for quite a while. It started actually during my PhD thesis, which wasn't meant to have anything to do with charm quarks initially. But then I sort of saw the potential that we have in LHCb of working with these charm quarks, and since then I've started that. At the beginning, we were less than a handful of colleagues getting started on that. By now, it's a huge activity with many very exciting results having been published. So as fundamental particle, definitely the charm quark, and as a sort of composite particle, I would still go with a D0 meson that I described earlier for pretty much the same reason.
So coming from a sort of more fun and less serious one to a more serious question. So what first interested you in physics, and what was your path into it? What kind of almost why physics?
Right. This was really, my interest was very much sparked in school. So I was extremely lucky to have a fantastic physics teacher who, what I really loved was all the experiments he did. And I was one of the people who didn't mind if they went wrong, right? So I accepted that this is part of the game, but he really put a lot of effort into that, and it really excited me how we can make experiments to test theories, to show that a certain relationship holds, and to measure something. And of course, making an experiment gives you the opportunity of making a better experiment and measuring something more precisely. So that was really what sparked my interest. And then I took part in a local physics competition, and through that got an internship in a nuclear physics lab near Darmstadt in Germany. And there I got to work firsthand on accelerators, but also detector development, and I mean that was just absolutely mind-boggling what was going on there. It was at the time a very exciting place, because they were the place where one of the world's leading places where new atoms, new nuclei were created. So these numbers, I think 113 was one of the ones that came about in the time when I was there, and it was just fascinating to be at such a place. And yeah, then that interest stayed. That was my first time there was actually just before I started studying, and then I started studying, and my first professor was a particle physicist. So that, together with the experience at the lab, just set me bang on course, and yeah, I stuck with it. And I must say I was very fortunate as well throughout the years, having had a number of chance encounters, really. So my PhD came about because I met my supervisor to be in the CERN restaurant, as many stories go. And I knew him because I had been an exchange student in Glasgow, where I did my PhD. And I bumped into him, and he said, "Oh, what are you up to? Are you interested in applying for a PhD?" And I thought, well, why not? I hadn't considered applying with you, but hey, so I tried it, and I got a scholarship, and yeah, that way, and a few other times as well. I just got lucky to be in the right place at the right time, because that is something that can be frustrating if it doesn't work out, and it doesn't mean that anyone is a worse physicist. I'm certainly not considering myself the best physicist around, but it's yeah, I was lucky enough to have the right doors opening at the right time, and that allowed me to yeah, stay with it, and by now have a fantastic team to work with.
So as well as you work in particle physics and also in teaching, you've done some work in outreach as well, in particular Blue Dot Festival. I don't know if you want to say some more about that, because I've got another question coming up, which is also related to outreach.
Right. Yeah. I mean that is of course always super exciting to be able to share what we do with the public. Right. The discussions about antimatter, the question what happened with the antimatter after the Big Bang. So matter and antimatter were created in equal amounts after the Big Bang, and now we're left with a matter universe with no antimatter around. So where has all that ended up, right? We don't really know, and that is a question that we try to answer with our research, and we know that within the standard model, even though we can describe matter-antimatter differences, we the effects that are visible there, that are known there, are far too small to explain these big questions. And that, of course, is something that excites a lot of people, and it's always great to be able to share that. And as you mentioned, at the Blue Dot Festival, I had the opportunity to share that with an audience of a few hundred people. That was absolutely buzzing to do something like that. But also, I think what I also try to convey in whenever I give a talk like that is the relevance of what we do to other fields, or the connections we have to other fields. Like I mentioned already, we have engineers and technicians working embedded in our team because we need these tight connections, right? And without absolutely fantastic and highly skilled engineers, we wouldn't be able to build these huge experiments, right? We'll probably not leave space for the cables or something like that, or let alone build a stable structure that can hold all these things in place and come up with cooling solutions and all that. So it's extremely exciting to share that with the public, and of course, at the end of the day, we're also to a large extent publicly funded, and is also a duty to then explain what we do, why we do it, why it's relevant, what can be gained from it. Yeah, luckily it's much more than a duty. It's just a great pleasure every time.
So the next question, for the most part, has been answered. It's kind of curious to you, what's the kind of core reason as to why physics outreach is quite so important?
Yeah, as I just mentioned, right? I mean, we have this duty, but also, of course, we want to excite the next generation, right? That's a huge component in that, and I think one thing that is absolutely key there is also to excite current minorities in the field, right? Obviously, we're one of the fields that has sadly still a very large gender imbalance. But not only that, there are a number of other minorities that should be much stronger represented, whether it's regional representation of physicists or what have you, and those are things where outreach events can help spark the interest of these minorities. And in LHCb right now, until like 15 minutes ago, we had the early career and gender diversity session of the LHCb week in our collaboration. That's a firm part of the plenary program, and thankfully we see the numbers going up. And I can say from my own experience, among our postdocs, we currently have a female majority, and it's just great. I mean, there's no reason not to hire female members of staff. I mean, I didn't bias, of course, the selection in any way. We just always hire the best, and they are out there. And it's great to have a diverse team. It's not just about the gender balance. As I said, there are other minorities, whether it's LGBTQ or as I mentioned, regional diversity. We've got those represented in the group as well, and yeah, it's just fantastic to be able to work with the brightest minds in the field. And I think, as I said, outreach plays a big role in bringing that message across and in attracting new talent and helping to reduce these imbalances.
So obviously at British Science Week, it's seeking to inspire students who are currently at secondary school, primary school, who are looking possibly towards physics. What would you recommend to people who have a kind of inkling towards it or might enjoy physics at school, who would consider a career in physics?
First and foremost, follow your curiosity. So you definitely should not have anyone tell you this is not for you, right? If anyone says that to you, just ignore them, right? So, but thankfully nowadays that there are so many supportive people out there, and I think that's maybe something to do is go and find someone who supports you. That can be your teacher, that can be someone in your family, or well, don't hesitate to drop someone an email at your local university or so, right? They may have the right contacts to put you in touch with a school outreach day or some event that allows you to get a bit more information and yeah, just keep your interest alive and hopefully growing, and yeah, just stick with it and follow your heart in that. And I think whoever is really keen on following that and digging in these areas, answering these questions with the tools that physics allows, is very much at the right place. So it's certainly a field for everyone, and the curiosity is a key thing there, and yeah.
Physicist, I'd like to thank you for taking part in British Science Week with UMPO, for allowing us to interview and talk to you. We greatly appreciate it, so thank you.
Well, thanks very much. It was a great pleasure.
Thanks for joining us for today's interview. We really hope you enjoyed it and that you will join us tomorrow when we meet another particle physicist, Yvonne Peters. Don't forget to like and subscribe and share to your friends. The hashtag is BSW21 and our social media accounts are @UOM Phys Outreach.